Start. Hi everyone, thanks for coming. Today's we have a CITA seminar by Nguyen from CITA at Northwestern University, and we'll be talking about applications of simulation-based inference to study near-field cosmology.
You spoiled the punchline, just machine learning in this slide.
Oh, sorry, it's not going to be simulation-based inference. That's a secret. It's going to be machine learning. Over to 3. Oh, there's still one slot left for dinner. If you want to join, you're welcome to join. Please sign up on the Google Sheet. And she also has some meeting slots left. So if you want to chat with him, sign up on the Google Sheet. Also. Over to 3.
Yeah. All right, thank you everyone. I'm a CITA fellow, and I'll be visiting actually New Toronto for the next month and not just a week. I'll be here until February. So let's talk about dark matter, machine learning, and dynamical mapping of dark matter. So first, with all astronomy talk, I want to show you a very beautiful video, assuming that this is loading. I don't know if the lighting here is good enough, but what it's showing you is like this one one central galaxy, in the kind of like the formation process where you see multiple smaller subhalos, smaller galaxies. It's kind of like in the process of merge into the central galaxy here. So there's a lot of interesting physics going on. But for the purpose of this talk, I will actually only focus on 2 sets of dynamical systems. The first one is intact satellites, dwarf galaxies, and the second ones are stellar streams, or kind of like the remnants of the intact satellite when they're about to merge with the host galaxies. So why do we care about these 2 objects? So one of the answers is dark matter. So you have probably seen this figure before from last week's seminar. This is showing you the roughly 80 order of magnitude in the mass range, the potential mass range of the dark matter particles. We know a lot about dark matter. We know it makes up roughly 80-something amount of matter in the universe, but we actually don't really know much about the particle nature of dark matter. We have a good idea that maybe it's CDM, but maybe it's not. There's a lot of debate on that. So the 80 order of magnitude in the dark matter mass can go anything from the -22 eV, so where the quantum limit actually kick into effect, up into anything like primordial black hole, like solar mass, tens of solar mass objects. And what stellar stream and dwarf galaxy is very good at is to help you probe this very galactic subgalactic scale. So I'm showing you here is the linear matter power spectrum, which is like the amount of clumping of matter as a function of the cosmic scale. So cosmic wave number, halo masses, depending on what kind of unit you want. With to this size, like the larger you go here, the larger the scale. So this is cosmological scale, and the more right you go in this figure is the smaller the scale, right? So I want to draw a line here and want you to focus on mostly a lot of these data points. So all of these are measurements, and these measurements come from the CMB, from Lyman Alpha Forest. So at the cosmological scale, you can see that this measurements align very well with CDM. Lambda CDM is very successful on this scale, right? But everything beyond that is the region that we have yet to actually probe. And it's even more, like exotic region in the linear matter power spectrum, where instead of like a scale suppression, instead of like fewer structure, you actually have a scale enhancement where you see even more structure at the scale. But typically these occur in the substellar halo or sub-Earth halos. So the region that stellar stream and dwarf galaxies probe is this kind of like this very region that actually looks quite small on the scale, but it's quite massive because it's cover both galactic and subgalactic halos. With dwarf galaxies probing the scale slightly larger than what stellar stream can probe. But this is kind of like the natural frontier, kind of like the natural next step. If you want to collect measurements on the linear matter power spectrum and test lambda CDM, this is the next step you will go. Right. So can you use dwarf galaxy and stellar stream to do this. So my talk will be divided in two. I will mostly focus on intact satellites and then a little bit on stellar streams. So intact satellites or dwarf galaxies are very low mass galaxies, very faint low mass galaxies. They typically don't have a lot of stars, typically don't have a lot of gas. Here is, I'm showing you a few example photos of dwarf galaxies. And the kind of like the curse of working with dwarf galaxies that you don't really have good photos to show people because they just look like a lot of stars. With some exception of the LMC, of the more brighter dwarf galaxies, where there's actually gas and star formations going on. As a matter of fact, these galaxies, so their mass range is anywhere from 10 to the 9, 10 to the 11, maybe 10 to the 8 solar mass for the dark matter halos, but the stellar mass is spanning 7 decks of magnitude, so like from 10 to the 2 to 10 to the 9, so very wide range of mass, right? And they're very faint, they don't have a lot of stars, and so what distinguishes it from, say, for example, globular cluster, the only thing is the dark matter halo. Dwarf galaxies are extremely dark matter dominated, with all of these systems are roughly about maybe 10 to the 9, 10 to the 10, like most of these galaxies around this. But you can kind of see the stellar mass here, 10 to the 7, 10 to the 6, 10 to the 4, 10 to the 5. So the mass-to-light ratio of this galaxy ranging from 100 to 1,000 in terms of order of magnitude, and is extremely dark matter dominated. So there's two types of dwarf galaxies. The one I will focus mostly on are satellite dwarf galaxies. A few dwarf galaxies, you can find them in isolations. Usually they would have more gas, they would have more star formations because they were not quenched by the host galaxies. But most of the time you find the satellite dwarf galaxies, when they were already post-infall into the host galaxies. Right, so as a matter of fact, there's roughly 60 dwarf galaxies, 60 confirmed / candidate dwarf galaxies in the Milky Way. This is kind of like the distribution of all this galaxy in the local group. So both the Milky Way, the Andromedas, there are dwarf galaxies of the Milky Way, there are satellite galaxies of other satellites like LMC, for example. And this number has been increasingly exponentially over time. That they start very small when you only have photometric surveys. But with the advance of digital surveys like SDSS, DECAM, Pan-STAR, Hyperstream CAM, this number has been recently skyrocketed. And it will be skyrocket even more with surveys such as LSST. So one of the core measurement interests of dwarf galaxies is their mass density profiles. So mass density versus the radius versus the distance from the center of the galaxies. And typically for mass density profiles, you want to find a way to parameterize them. This is the density profiles of a dark matter halo. And typically on functional form you see, even though this is not a unique way to model this, is the generalized Navarro-Frank-White, which is this equation here. But within this equation, I want to point out one very important parameter is this gamma here, is the inner slope. The inner slope of the dwarf galaxies are extremely important because, first, that they extremely sensitive to the dark matter physics models. So I'm showing you here 3 profiles: a CUTS profiles, a core profiles, and what I just call super CUTS profiles for lack of better names. Core profiles mean that the density flattened into a constant core at low radii correspond to gamma equal to 0. And this can be created by self-interaction dark matter. For example, with cold dark matter, typically you see some kind of Cauchy density profiles when the dark matter density steeply rise as you go towards the center. So gamma equal to 1, and this is without any influence of baryon. And there's some more dark matter models, a more exotic dark matter model like distributive self-interacting dark matter, or just even normal dark matter, self-interaction dark matter itself can even collapse and create this kind of like very, very cushy profiles, even more than cold dark matter. The second reason is that all of these density profiles are extremely sensitive for direct detection experiment, which is seek to measure the signature of dark matter annihilation or decay. So dark matter annihilation into standard matter, or or decay into standard matter. So this density profiles affect the flux of this annihilation and decay, which is the prime objective of this direct detection experiment. So when you look at density profiles in dwarf galaxies, you run into many problems. I like to just call them the density profile problems, but you might have heard the Caucus problem, the diversity problems, many names. Example here is the mass density profiles versus the result, the radius from the center, from the Littleton surveys. And you see a bunch of all of these data point, the measurements of the density profiles of dwarf galaxies. And this entire a bunch of curve here, this entire solid curve here is dark matter only simulations. So dark matter only simulations predict some kind of NFW profiles. It's very steeply rising curves, cuts. Even though most of the dwarf galaxy that you observe it has a core profiles, a custody profiles, or a diversity of density profiles. And you might want to invoke baryon feedback to kind of solve this problem, because historically we know that baryon feedback can kind of like flatten this custody profiles into a core profile by pushing the matter outward, by injecting energy into the system, right? But remember that these are dwarf galaxies. They don't have many gas, they don't have many stars, they don't have a lot of signature of strong star formations. So how much baryon feedback do you actually need to push a custody profiles to a core profiles? And if you change and you increase the baryon feedback too much, then you run into problems with all the area of astrophysics. You run into problems with stellar halo-mass relations and all that, right? So baryon feedback, you can invoke them, but you have to tune them into a very specific value, and it's also very uncertain if it can like fully resolve this density profile problems. And that kind of gives rise to a lot of the alternative dark matter that I showed in the previous slide. Give the motivation for a lot of these dark matter models. Right, so, and another problem is density profile is actually very difficult to measure. So how do you measure density profiles? I'm showing you here a very scary looking equations, but if you just divide them into two parts, this equation is known as the cheese equations. And what it does that is related this term, this right-hand side term, which is just a potential, a mass term, the potential term, with this very complicated term that's actually just a pressure term, right? So this is the cheese equation. It's related to gravitational potential to some kind of pressure, and this is the pressure is coming from the velocity dispersions of the self-gravitating system, right? And the entire point of cheese modeling, of mass dynamical modeling, is to find a way to relate what you can observe, the radial velocity dispersions of member stars in the dwarf galaxies, to the dark matter density profiles. This is the entire objective of cheese modeling. But before we move on, I also want to point out this very annoying term. It's called beta R here. In this analysis, this is the so-called nuisance parameters used for the use of statistical terms. So this is called the velocity anisotropy profiles, measuring how isotropic, how anisotropic this stars in this dwarf galaxy is. And this profile is entirely sensitive to either the formation history of the galaxies, right? So typically when you're trying to measure dark matter density profiles, you don't usually care that much about this. But this is actually the problematic terms. Right, so gene modeling has many limits. One of them is the anisotropy profile, which I will go over in the next few slides. But if you take a look at this example, where in this 2022 studies, where China and DSIP trying to fit the genes modeling on a bunch of very idealized systems with roughly 100 stars, you can see that you get almost no constraint on this inner slope here. The error bar on the slope is gamma plus minus 1. So you cannot really distinguish between cusp and core with only 100 stars. And I believe this is the case where you don't have measurement uncertainties at the same time, right? And this number of stars is, this is the number of stars that typically for ultra-faint dwarf galaxies, for classical dwarf galaxies, you can get spectroscopic membership of maybe roughly about 200, 1,000 stars, 2,000 stars if you're lucky. So you're dealing with regime where you really have very, very few tracers, and genes is not very effective in that. You only have line of sight velocities too, and that also gives rise to a bunch of problems. And another set of limitation of gene modeling is one is to even get the change equation in the first place, you have to assume dynamical equilibrium and that the system is in spherical symmetry. You don't always have to assume spherical symmetry. You can kind of like invoke some kind of triaxial halo in G's modeling, and that will still work. But for most of this talk, what I want to focus on is this relying on the velocity dispersion, the light upside velocity dispersion alone, which gives rise to the so-called mass anisotropy degeneracy. So what is the mass anisotropy degeneracy? So I'm showing you a picture of both galaxies. This is the anisotropy. This is the equation, the G's equation, but rearranged so that the anisotropy term is kind of like just stand on its own, and you can see how it's related directly to the mass term, right? So if you, for some reason, if you underestimate or overestimate this anisotropy term, then you will underestimate or overestimate the mass. So the degeneracy is coming from this, because you only have the light upside velocities. If you look at the center of the galaxies, you know what the light upside velocity measure is the radial velocity dispersions, right? So like kind of like the dispersion into the page here. If you look at the edge of the galaxies, now what you actually measure with the light upside velocities is the tangential dispersions, right? So to go from here to here, if you don't assume a functional form of the anisotropy profiles, you cannot really distinguish between the change in anisotropy versus the change in mass density profiles. And this is the mass anisotropy degeneracy, and one of the biggest limitations of the current G modeling. So there's multiple ways that you can break this. So you can always use extra informations. You can use proper motion. If you have proper motion, then you can measure beta R directly. You don't have to rely on light upside velocity anymore. And you can break the mass anisotropy degeneracy in that way. You can use multiple tracer populations, meaning that you take your galaxy, you divide your stars into two populations of stars, maybe a population of younger stars and a population of older stars, and they all live in the same potential, but they might have slightly different anisotropy. And you can use that to just only constrain in the dark matter. But the main thing I want to focus on is the higher order moments here. So what does it mean by using higher order moments? So first, defining the distribution functions as just describing the phase space density of the tracer stars. The distribution function should encode all measurable kinematic information in the system, right? As a matter of fact, the G's equation that I showed you in the previous slide coming from the collisionless Boltzmann equations that I'm showing here, which is just the derivative of the distribution functions. And the velocity dispersions is simply the second moment of the velocity phase space here. So higher order moments, meaning that instead of only using the velocity dispersion, you will try to take this distribution function and you look at the higher order moments, maybe the third or fourth order moment of this. And that's give you extra constraining power for this. But what if you can just use the distribution function entirely? What if you don't have to do any integration? You don't have to rely on any extra order, higher order moments. Just use the distribution function as it is to do your constraint. So can we use machine learning to do this? Yeah, so the kind of technique, the problem that you're trying to solve is you're trying to solve the inverse problems where you're trying to map from the velocity dispersions back to the dark matter density profiles. Simulation-based inference is an inference technique, is trying to solve the inverse problems, but instead by constructing analytical likelihood or using traditional Bayesian approach to do this, it basically just relying on simulations at that's the implicit likelihood. I won't go too much into the machine learning part, but feel free to ask me about a lot of this in the discussion or afterwards. All the names you might see is likelihood-free inference, which I think is a very bad name, implicit likelihood inference, and it has application in many fields of physics and astrophysics. And even rising more recently, I made this slide a few years ago, so there's even more work on simulation-based inference recently. So just to draw a comparison between traditional Bayesian inference versus simulation-based inference, typically when you want to do inference, when you're trying to solve the inverse problems, you start with some kind of prior distributions, which encode your prior knowledge of the parameters of the system. Here, the parameters is the dark matter density profiles. as well as any other parameters that you don't care about, like the anisotropy parameters. For example, you want to construct a likelihood, you ask, like, you look at the observation, you say, how likely is this data given this, like set of parameters. And you can use Bayes' theorem to construct the posterior probabilities. So the probabilities of these parameters given the observations that you have, right? And with traditional Bayesian inference methods, what you would do is usually this term is very high dimensional and very difficult to infer analytically for the entire parameter space. You would use some kind of sampling technique like MCMC, that's the sampling to sample the posterior distributions. With simulation-based inference, you kind of take a different approach. You always start with the prior distributions. You sample some kind of parameters from these prior distributions, and now your likelihood becomes your simulation, which is like the implicit likelihood. The difference is that you don't actually have to be able to evaluate this likelihood at all. That's why it's called implicit likelihood. You only need to be able to sample from this likelihood. So with simulation-based inference, you would draw a sample from your prior. You would use the samples to draw more samples to draw the observations or the mock observations from your simulation or your implicit likelihood. You construct a training data set, and in modern days, you use neural network to approximate the posterior given this kind of training samples. And there's multiple simulation-based inference actually range back to like very, very old times where people still do something called approximate Bayes computations. But most modern days, you can see people mostly using neural simulation-based inference with neural network to try to use neural network to approximate these posterior distributions. So Kai Kramer has a very good summary on simulation-based inference here that I will refer to you. But the set of technique that we do for both this intact satellite and the stellar stream work that I will show you is neural posterior estimations, where you use neural network to directly estimate the posterior distributions given some kind of joint distributions of the observation x and the parameters theta. And generally, as I mentioned, you start with the prior distributions and you want to construct a data set, right? So you always usually first step is data set generations, where you define the prior term and then you define your simulation, which is your implicit likelihood, right? You put it to some kind of density estimator, and I can go over density estimator and all of this in much more details in the questioning, but in a way you can think of it as like you just feed this density estimator, which is the neural network that can approximate distributions, samples from this joint distribution here. And the more you sample the joint distributions, the better the neural network is, the better the neural network learn, right? And yeah, so you just give a sample from this joint distribution, and slowly, with some kind of machine learning magic, you can kind of like, you learn this density estimator, which in this case is the posterior. And there are multiple approaches where you can learn the likelihood instead, you can learn other likelihood ratio instead, that I won't have time to go over. Then from this density estimator, if you have a new observations, then you can just use this estimator to directly evaluate the observations. And the advantage of this, the two biggest advantage of this is one, right, like I mentioned before, you don't really need to be able to evaluate this likelihood. You only need to be able to sample this likelihood. So the likelihood can be extremely complex. So the simulations can range anywhere from analytical simulations to n-body simulations to anything that you just cannot write an equation out of. So this is one big advantage of implicit likelihood type methods. The other advantage is that, at least with this setup, when you have a new inference, you just give it a new observations data. This is called amortizations. You don't have to rerun the algorithm again, so that saves you a lot of time. So we use this framework, and we're trying to see that, okay, now can we generate sample from the phase space, and then we can feed that into a neural density estimator to estimate, to approximate the posterior distribution from them. So of course we have to talk about the simulations. So how do we create the simulations? So we can define the simulations for the dwarf spiral completely analytically without invoking any hydrodynamical simulations, simply you can just have a dark matter profiles, surface brightness, and velocity anisotropy. So all of these are your parameters. From all of these parameters, you can use the Eddington inversion formula to go from this to construct a phase-based densities, right? So this is your theta, this is your simulations, which is just the phase space. And remember, in the setup of simulation-based inference, the simulations is also the likelihood. So this is kind of roughly the same with running Bayesian inference with this likelihood. And this likelihood is the phase space with full kinematic data. So without any loss of information coming from taking this phase space and do a second order integral to get the velocity dispersion, for example. And you can sample it directly from the observed stellar. And you can sample it directly to get your stellar kinematics, and you can treat this as your samples. And you can fit all of that, both this set of theta parameters here, the dark matter profile, surface brightness, velocity anisotropy, and the observed stellar kinematics, and you can combine them to into the neural density estimator. But one question that you might also thinking about is that, okay, now if you actually have a distribution function, why not just use this as the likelihood directly? And indeed you can, right? This is called distribution function mapping, distribution function matching, depends on what terminology you want to call it. But there's some caveats of that. One is typically when you do that in the Bayesian way, this distribution function here is always in the 6D kinematics. So if you lose the information, like if you have incomplete kinematics, like you don't have proper motion, you don't have all the you only have projected coordinate and not distances, then take into account this incomplete kinematics information is possible, but very tricky and also very expensive. Distribution function mapping the Bayesian way is also very expensive. It's not amortized. You only can really do it once, and you have to rerun it for each observations. And the most important thing is the equilibrium assumptions. So you actually don't usually operate on the phase space, the 6D phase space. What you want to do is you want to take this x and v here, you want to convert it to integral motions, like energies, like action angle, like angular momentum, and you construct the phase space on that, and that's actually where you evaluate the phase space on. But the act of doing this integral motion, meaning that you will assume the equilibrium assumption here. And so that will only work on limited case. So for most of the dwarf galaxies work, I will mostly dealing with the equilibrium assumption case, but I will show you in the stellar stream how this can be extended to equilibrium dynamics. So this is an example of stereo distributions from the models. So as a reminder, we take all of that, we sample stellar kinematics, we train a neural posterior estimator on this, and what the posterior estimator gives you is the posterior. So you get in the slope, the radius, the entire multiple dimension posterior distributions. And here is showing, I'm just showing you a 3D corner plot where the black is the true data point. And you can also convert that to density profile, mass profiles, and then compare them with observation or abstract physical information out of this. But this is only mostly on training simulations. So how does it actually work on non-training simulation? Because ultimately, the goal of any of your algorithms is to work on real data. And machine learning is notoriously generalized poorly on out-of-domain data. So any machine learning algorithm that you train require very, 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 very extensive stress testing. And one of the tests that we do is, so our simulation has nothing to do with hydrosim. What if we test on hydrosim? We already know the answer. So we took the fire simulations, we take host galaxy of these simulations, the zoom-in simulations, and we extract all the satellite of these simulations. So this includes satellite that is in very nice equilibrium, satellite that is barely stripped, satellite that's actively undergoing tidal disrupting. So there's a very wide realistic environment of satellite here. And we see, can we recover the density profiles from this? What kind of extra information can we recover from this? And this is an example. So
could I just ask a quick question? So, are you taking, you mentioned the issue of velocity dispersion and assumption before. Is that being included in this? That is to say, the anisotropy of the distribution, especially for these small objects? Or are you enforcing spherical symmetry for the density profile?
We simultaneously fit the density profiles and the anisotropy profiles. So we assume a functional form for the anisotropy profiles, specifically the OSIPCA merit density profiles. We have to assume some kind of functional form, but it's not constant.
Is the anisotropy changing as you go out in the galaxy?
Yes.
And that's a lot of information to try and draw. Is that really useful?
So I can't.
You can get it from the simulations, but it seems to me very hard to get from observations if you ultimately apply this observation.
It is very under constraint on real data anisotropy, and it's under constraint in the simulations too, because when you project the data, you lose so much information on that. I'll have a slide on real data that I will show you, and I will show you how poorly constrained anisotropy is. Okay. So just going back to the slide. So each of these panels is density profiles versus radius. All the data points, all the black data point that you can extract directly from the simulation. Each of these are just like different satellites of the host galaxies. When we test them both on CDM simulation and SIDM simulations, I run both the genes model, a very simple version of the genes model that I can go into more details, and as well as the neural network models, the neural posterior estimation models. And what very interesting that you see is that at very large number of tracer, the models actually agree very well. This is not surprising because the more stars you have, the more tracers you have, the more extended the tracer you have. You actually break the degeneracy a little bit by having stars at the outer radius for dwarf galaxies. So the model should, genes become more robust, the model should agree with each other. But when you move to the lower number of stars, then you see this is where the extra kinematic information start to become more and more valuable, where you see the model gradually outperforming genes, especially in the cases, for example, when you only have 35 stars, where the uncertainties of this model is much better, and also the fit also align well better with the black data point. And the 35 star is the Olger Henry gene. I put like the stars here is because fire actually doesn't capture any of the Olger-Feng dwarf. The Olger-Feng code regime that I mentioned here is purely on the number of tracer and not on the properties of the galaxy itself. And you can do more stuff. You can do more tests on this, right? Remember, one of the advantages of this model that is armatized, you can test it on an extremely large number of samples and know how it behaves. So you can separate this set of galaxies, and I think there's about 100, 200 something galaxies here. So I divide them into samples of tidally disrupting galaxies and more tidally disrupting galaxies based on their properties. And you can run the model on them. And on the top panel, I'm showing you the peak circular velocities by the truth value versus the predicted value. And then the bottom panel is the pre-informed mass, a virial mass. And we can show that you can get both the structural parameters, both the peak circular velocities and the pre-informed virial mass quite accurately. Do you have how much time do I have?
20 more minutes.
Nice.
22.
Okay. Yeah. So this is, surprisingly, this is one of the first comparison where someone actually take a bunch of mass modeling methods to try to recover Vmax and M200 in like realistic environment. So people have done this in the past, but mostly on M-body simulation, nobody have included Lagrangian in this. So this is the first study that does that. The machine learning part is just a bonus. I think I'm not sure if you're going to be excited about this, but this is the data that he sent me. So this is very preliminary data, very preliminary result. I take the liberty to run on Carina too, but he mostly sent me Draco. So this is two dwarf galaxies, one on the Carina dwarf and one on the Draco dwarf. So this is real data. This data is coming from the Walker's 2023 catalog that is taken from Magellan and AMT data. So I'm showing you four profiles here for two different dwarf galaxies. Density profiles, the mass profiles, which is basically just the density profiles integrated, the anisotropy profiles, and as well as the velocity dispersion profiles. And all the black data points and are from the actual data. And you only have the black data point for the velocity dispersion profiles because this is raw data. You don't actually know what the velocity profile is. And yeah, and you can kind of see. So each of these, I think this has like roughly 500, and this has also roughly 500 traces stars. This is the region where trees is supposed to be like roughly the same with the models. So you can see a lot of like the profiles kind of like match each other very nicely, and the mass profiles. And there are cases where they definitely don't agree. And usually this is in the regime where you don't really have a lot of data, and usually only for the inner profiles, for example. So this is the anisotropy profiles, right? And it can go from anywhere from I think -1 to 1. With 1 is radial anisotropy, and 0 is isotropic, and -1 is tangential anisotropy. And this is only the 68% confidence interval. So if you plot the 95% confidence interval, it will cover the entire range. So this anisotropy profile is still extremely poorly constrained, even with 500 number of tracers. And using from the anisotropy and the mass profiles, you can calculate the velocity dispersions. And you mostly do want to do this as kind of like a check, because to see if your model fits your data very nicely. And in cases like both Karina and Draco, you see that the models actually go into the data nicely. She slightly overestimate the velocity dispersion here a little bit. I'm not 100% sure why all of this is very, very preliminary. I just found it over last weekend, but this is something that we should keep in mind when we report this. So the method also kind of worked very nicely on real data. So the next step is, well, I'm going to tell you the next step at the end of the talk, but the next step is to run on more galaxies and on the full Walker's catalog, and then trying to push the boundary for it to ultra faint.
Okay. So can you just go back and, my eyes are used to this, walk through that anisotropy figure. Where is the origin?
The origin?
As one moves out in the galaxy, or is this a global quantity?
So I have a hard time.
Typically what happens,
yeah,
the baryons will have quite a different anisotropy distribution than the dark matter.
Yeah.
And the baryons tend to be more spherically symmetric.
Mm-hmm.
And they're more symmetric in close than further out. And so, am I seeing that on that anisotropy figure, or the dispersion is so large you can't tell?
So the dispersion is so large, but you can still see the mean behavior, right? So beta equal to 0. So this is this is going to the center, and this is going to the edge of the galaxies, right?
Okay, so you get a tendency for a non-zero beta in the outer part, but it's mostly 0 beta with very wide dispersion.
Yes. Yes, indeed.
And then the errors are all determined by the learning set that you have. That is to say, it's restricted to the number of galaxies you have. Are you confident in the error bars? Because one of the problems, in my view, with AI and machine learning is that characterization of errors. So it's not always that clear.
Yes. So for this one, I'm confident about the error bar. The reason is that because I tested previously on the fire, but there are tests that you can do with the error bar. So you can ask yourself, for example, if you produce a 68% confidence interval, and if you run a large amount of sample, does that actually cover 68% of the true value? So you can do this kind of frequentist test on this. So you really only know that your model is produce the right error bar by very extensive stress testing. That's why I stress a lot on the testing of the models. But I know this from testing, but I don't have the figure to show immediately here.
So if you don't mind, one more question, which is related, which is that you did split between things that look like they might approximately be in equilibrium and those that might not be. Was that done by machine learning, or was that done by human learning?
That is done by Tim and me. That is done by me and Tim. No, like we process the data before we feed into the model.
Right, so
Yeah.
you've already done that selection.
Yes.
But if you were imagining the neural network, it should be able to do that sample split itself if you gave it enough degrees of freedom in terms of its flow down to its minimum. Or is that not feasible at this stage?
At this stage, I think my intuition would be to say no, because the sample that you train it. So if you want to understand the model, you have to look at the training sample. The training sample only have equilibrium, only have star in equilibrium. So I think that if there's a significant amount of stars in non-equilibrium, the model would break down. I think it's just like how much is the tolerance of that.
Can you test this against different types of globular clusters, most of which probably don't have dark matter? You have very different, data sets.
So I have not tested on global cluster. I do have a data set on one global cluster that I haven't taken a look at.
Some, like Omega Sun, might have dark matter.
Yeah, for some, yeah. I think my worry of testing on global cluster is that the size of them is a little bit too small, and my prior distribution actually doesn't cover like a typical size of the of a global cluster. So global cluster is too dense for the models to work on right now, but I haven't tested on yet. Yeah. So moving on to the next part of the talk. So on stellar stream modeling, so this is roughly similar concept of satellite galaxies, trying to map from the phase space of stars to something dark matter related, even though the actual process is completely different. But the system here for a stellar stream versus the dwarf galaxies, a stellar stream is not really in equilibrium at all, right? Right, so I'm showing you here as an example of a stellar stream. So stellar stream or tidal remnants, either dwarf galaxies or global cluster. Global cluster can also be stripped from dwarf galaxies. And I'm showing here is the Auriga simulations where we can kind of see a stellar stream being formed. It's going too fast for me to point out a lot of the features of stream, like the trailing arm or the leading arm and all that. But you can kind of see just like a stream pattern here. So on the sky, this is what they actually look like. This is a bunch of stellar stream, but it just look like some kind of like overdensity on the sky. And if I want to point out a few streams that I can detect it, these are a few example streams. Right, the Orphan Sagittarius, which I think is the biggest, longest stream that we detected so far, and Paloma 5. And this is from SDSS data. So there's roughly 100 streams that are detected now. Shown here in the figures is from DES, from Ship et al. In 2018. Only showing you 15 streams, but this number is very slowly increasing to roughly 100 stellar streams. So how does stellar stream related to dark matter? So if you look at these two pictures here, where I'm showing you the dark matter density, just the density map of dark matter with the central galaxy here. This is the difference between CDM and warm dark matter. So warm dark matter, they have lower mass, they move faster, so they wash out more structure. They have more, quote unquote, small scale suppression. So within a warm dark matter map, you will see like density profiles, or just density distribution, very, very smooth. While CDM is very, very clumpy, right? And each of these, the big circle, let's say, for example, the dark matter halo of the central galaxies, with a lot of the satellite, for example, observable satellite is centered within the smaller circle. So you can see how the density in warm dark matter, density map in warm dark matter versus cold dark matter is very different, right? But the number of observable satellites is actually not much different. And this also depends a little bit on how you count them. but the numbers here are very statistically not significant between cold and warm dark matter. So what stellar stream helped you do is when a stellar stream being accreted into the central galaxies, it will orbit this galaxy multiple times, right? And during this time, it will interact with all of this structure, invisible or not invisible. So it will interact with all these subhalos that is not massive enough to form stars, and eventually will create structure in the stellar stream. An example of a stellar stream that I care a lot about is this Atlas and Liku-Uma stream. There actually used to be two streams. If you look at this previous map here, you see Atlas, Liku-Uma, and Atlas. They used to be different streams until I think Tin kind of like connect them together into one single stream. So why do we think that they want two separate streams in the first place? It's because they have this like discontinuity here, so-called kink, right? So we think that this kink is in the stellar stream is due to like a collision with a very massive dark matter halo. But of course, you don't just have one collision with one big subhalos. You can have multiple collisions with multiple smaller subhalos, and that can create over densities or under density within the stream. Like in a CDM regime, a stellar stream will be more clumpy than a warm dark matter regime, where the stream will be much more smooth. So this is showing, actually, just to explain the axis, this is just showing the stream coordinate and the velocity and the distance of the stream. So typically for stream, you want to project the term of the coordinate along the stream. So this is just some kind of like coordinate transformation of RN depth back to the stream coordinate. Well, each of these are like the field of view of the telescope and a bunch of like member stars. So we think that Atlas Liku-Uma is being disturbed by by some kind of subhalo. And if I would draw an unperturbed stream, it would look roughly something like this, right? So this is some kind of measurable features in the phase space that you can use that to map back to the properties of the dark subhalo. So assuming that this is collision of the dark subhalo, and this is saying a lot, assuming a lot, because this kink can also be created by multiple order effect as well. So can we use this to infer the properties of the subhalo? So we can roughly do the same, right? So we can use the same models to do this. Let's say you generate a bunch of streams, you interact them with dark matter subhalos, you have some kind of measurable phase space. Can you use that to like learn the properties of a subhalo? So there's a lot of previous work on this. Specifically on Atlas Liku-Uma, nobody has really applied this on real data yet. The closest anyone has come to this is Derek Hilmy in 2024, where he take a lot of mock simulation of this Atlas Liku-Uma, and he applied MCMC using the 1D Gaussian likelihood to kind of estimate the properties of a subhalo interacting with this mock AAU stream. And this is an example of the simulations. This is just showing the stream coordinate. You can see the kink very nicely here. This is the mock simulations that with the parameters handpicked by the simulators to match roughly the Atlas and Liku-Uma stream. So all these parameters is handpicked, right? And it's just trying to match the stream. And the progenitor of the stream is probably around here, right? So what they do is they would take this stream, they would bin this into a 1D, right? And they would use the at the likelihood, right? But I will show you in the next slide why you can't really do that, because the stream morphology is too complex for that. And also the width of the stream is not Gaussian, so you cannot use a Gaussian likelihood for this. An example is this, right? You can have one stream that looks like this and another stream that's very curvy looks like this, that does not really fit in the 1D Gaussian space, right? And the thing is, the parameters of this stream are not actually that much different from each other. This is roughly similar magnitude of perturbations, but the stream can look completely different. And there's also multiple features like this bifurcation here or the spur here that means that you cannot just evaluate this with 1D Gaussian likelihood. So it's better, I believe, is to use some kind of implicit likelihood methods to do this, or maybe trying to approach with a 2D Gaussian or some kind of more advanced method. But this kind of inference is still roughly new, so not a lot of work has been attempted on this yet. And similar with dwarf galaxy, you have simulation of stream halo interactions, I think for the interest of time, I might have to skip this part. So we basically evolve a bunch of stream and as a payload in a common potential, static potential under the Milky Way and LMC. And we evolve them as a function of time, and we create simulations from that. And we use these simulations to put this into a neural with their estimations to try and measure the properties of the payloads. And we're actually not the first people to do that. So in the previous work, the U Toronto group actually have done a very similar studies, but on two parameters, the mass and the velocities of the GD1 stream, not the Alice stream. And then they report the posterior distribution and compare with traditional techniques and find that NPE have the potential to very improve the constraint on the stellar streams. So one thing I want to point out here too is the degeneracy between the mass of a subhalo and the velocity of the subhalos. So the subhalo is kind of like a bullet going to a stellar stream, right? So the faster the subhalo is, the less time it's going to interact with the stream. So the less strong the perturbation is, and the more massive the subhalo is, the more massive the perturbation is. So in our work, we actually do roughly the same thing, but we apply Atlas Oliguruma, and we try to explore the parameter space of this Atlas Oliguruma a little bit more. We try to constrain both the mass, the radius of the subhalos, which can be used to measure concentration. That's important for galaxy formation studies and dark matter study somewhat, as well as other geometry properties of a stellar stream. So we run this on. So we have multiple models on this. We start by generate very idealized cases stream. So a stream with an observed number of stars, 10,000 stars, no measurement uncertainties, that you can see multiple 6D coordinates. And we try to vary this coordinate completeness to see how the model would react. What's the constraint of the subhalos? If you only have 5D data, what's the constraint on the mass of a subhalo? If you have 2D or 3D data. And we also test out more realistic observational scenario where what if we have 6D data, like in the S5 case, and then we do projection for LSST year 1, LSST year 1 plus HOMOS data, which is the spectroscopic surveys, and the combined posterior distribution. So this is some, for example, the number of stars you see within the present year, the upcoming year. For AEU, the public data has roughly 100 stars. And the projection for LSST is that in the future, you're going to have roughly 4,000 stars with LSST, but with only 5152 coordinates. And if you include LSST and spectroscopic survey, you can get roughly 400 stars with 60 kinematics. So I'm showing you a fraction of the result, but I'm happy to talk about it more. The first set of results is how you can recover the subhalo mass. So we find out with 6D data, you can kind of constrain the subhalo mass of a 10 to the 7 subhalos to roughly 20%. For 6D data, if you have everything, and 2D data is 35%, where you only have the coordinate. So basically, only photometry data. And this is only on a mock Atlas Oliguruma. Nobody, including us, has applied this on real data yet. And I'm showing you the constraint, so that's these parameters. I'm showing you only the 2D corner plot of the subhalo mass versus radius versus the mass and the total velocities. I'm showing the total velocity mostly to show, again, that this degeneracy, this very strong degeneracy here, especially in the 2D cases. And the performance is actually much worse if you include uncertainties, because with more uncertainties, your data obviously become more uncertain, but also more importantly, you'd also lose a lot of stars. In the idealized case, you have 10,000 stars, where in the present 6D case, in terms of S5, you only have 100 public data stars. So the constraint is much worse, where we show that with this kind of framework, you can get 80% constraint on a 10 to the 7 subhalo mass with the present data. And in the future, if you have LSST and if you have HOMOS, I know it's not a very fair comparison because I should also include more present day data. You can get this number down to like roughly 45% with uncertainties. All right, so I'm going to skip this slide. And I just want to flash this is that I'm saying that nobody has run it on the real data yet, but that's actually not entirely true. So one of my students is working on this, and this is the very, very, very preliminary result of this model working on the public AAU data. And this is the entire 6-day corner plot. I'm running out of time, so I won't have time to go over all of this, but I'm happy to chat more about this. And there's a lot of caveats on this work. One is that you definitely assume the disruption for the subhalo, which is not true. This subhalo can create, the features can also be created by time varying potentials or any others effect that is very, very tricky to models. We do not also consider a lot of parameters like the impact time, the impact angle, or the progenitors, for a reason that because they expand the parameter space too much and everything becomes too expensive, and they're also very, very tricky to models. So in the future, the things that we're kind of working on right now is to improve the simulations using non-static potential, improve the models of the particle ejections, and we also plan to improve the uncertainty models, as well as using things like bigger training data set, bigger machine learning models to explore, to get better constraint on this. Right, so I have talked about stellar dynamics and how you can use stellar dynamics in dwarf galaxies and stellar stream to apply constraint on dark matter. And in the future, it's very exciting for diffuse cosmology because you have many, many photometric surveys coming up, like like LSST and Roman, that can give you both the photometry data, discover new ultrafine system, new stellar stream, as well as providing you with stellar proper motions. And with new spectroscopic data, you can have better radial velocities to both more member stars with radial velocities and as well as more accurately measure radial velocity as well. And I'll give you with the main takeaway, and I'll answer any questions.
Thank you for the wonderful talk. Yes, we have probably time for one question. Sir?
Great. I'll use my one question to talk about streams. Your second point here says that you can reconstruct individual subhalo stream impacts, but very few streams have like obvious kinks or breaks like GD1 or AAU. How could you use the SPI method for cumulative impacts from small for just general stream heating, like all streams should have, or do we have to find like the perfect streams with breaks in it?
So not with this model. This model is designed, the entire analysis of this model is designed so that you assume like one very big impact and you kind of ignore the rest of the impact. You kind of just assume that they're negligible. But if you want to model the entire spectrum, the entire subhalo mass function, then you need to be able to simulate the entire subhalo mass function. And we actually have a project going on that. But it's just not something that we explore for Atlas and Luku-Uma. I think this is more reasonable to do for like GD1 and Atlas and Luku-Uma. Chris?
When you consider the interaction of the subhalo with the stream, say, well, the subhalo mass, but subhalo is a mass distribution. Depending on the size of the subhalo, would you be more sensitive to some part of that mass distribution? Would some part of that mass distribution have the biggest impact on maturity in the stream?
That's a great question, but I don't know the answer on top of my head.
Open parameter, the size, the mass, the parameter is open
Well, sure, but when you say subhalo mass in that parameter, that sounds like you're treating like a point mass. Subhalo has a mass distribution. And, depending on the mass of the subhalo, right? It could be that maybe the core of the subhalo is more important.
But there is a density. There is a density profile open subhalo used in the simulation.
Of course, but practically speaking, one can ask when you look at the perturbation that is part of the stream, and you say change the subhalo mass distribution. How much sensitivity is there to that? I guess that's another way of asking the question.
So we have not tested that explicitly. We assume some kind of mass isolation. Well, we assume some kind of mass isolation. So previously we assumed like Blummer for the mass, and I think that's really bad. But if you assume that, then you can actually constrain things a little bit better, but that's wrong anyway. I think the best way is to probably just either have a very parameterized version of the subhalo with with large degree of freedom and trying to constrain all the parameters. Or we just have to like test out multiple set of parameters, like maybe a plumber and maybe an NFW for one, and we do multiple type of constraint. And if you're only interested in about the mass, maybe you can treat everything else as the nuisance parameters.
It sounds like a wonderful topic of discussion. So let's move upstairs and continue it because we're out of time right now. Sorry, I'm not pausing it. Let's just move upstairs and have desserts and enjoy it while having discussions. Thank you everyone for coming.
Actually, I have to go to my next meeting. We can check tomorrow.